Okay, welcome back. So we were discussing properties, and we'll continue the discussion. We'll take another example, an example of saturated liquid water of mass of a 200 gram, which is completely vaporized at a constant pressure 100 kilopascal. So what we have to determine is the volume change and the amount of energy transferred to the water. And the idea is to make use of the tables in order to solve the problem. Okay, so let's look at it. What kind of table we should see? We have been given 100 kilopascal as a constant pressure. So essentially we should take a look at the saturated water table A5, okay, because you have the pressure. So let's look at it. So the idea behind this question is that you have a saturated liquid water which is completely vaporized, which means at 100 kilopascal this fluid is vaporized to the gas or the vapor, and then we need to find out the change in the volume. So let's look at the table again. So this is 100 kilopascal, table A5, okay. We are looking at the pressure, and the corresponding 100 kilopascal, the saturated liquid value for the specific volume is given here, and as for the corresponding vapor is here, okay. So we are going to make use of these two values, and then we going to plug in. So we find out the difference because we wanted the change in the volume, okay, but this is per unit mass. So this difference is given in this form. So then we need to multiply this value which we found, or which we based on the table, by the mass of the saturated system, which is given as 0.2 kg, and thus the total volume can be calculated. So that's a part one, how to find out the volume change. What about the amount of energy transferred? In a similar line, you can also find out first the HFG, and then you multiply by mass, okay. Then let's look at again the table here. The corresponding 100 kilopascal, the HFG is given already. This is the evaporation enthalpy, and this is the value is already given to you. So we just take the value, we multiply again by mass, and we get this value, okay. So that is how we are going to calculate the total amount of energy transfer to the system in order to vaporize. So as we already discussed in the last lecture, there are other fluid tables available, that is for saturated refrigerant. Now let's look at now the superheated vapor case, okay. This is the case where it is going to be away from the saturated vapor line, in the right side of the saturated vapor line, and at a temperature above the saturation temperature. So what does it mean? That means let's say you take a pressure, the saturation temperature is here, corresponding to this pressure 0.5 megapascal. So this particular point, which is represented by the circle, the temperature here is greater than T sat at 0.5. So this is indicative of superheated vapor, okay. And it's also very much obvious if you look at this diagram that enthalpy of superheated vapor should be more than the corresponding value at saturation Hg. The reason is that you have also imparted more heat to the system, and apparently that is transferred into the enthalpy. Okay, so at a specific pressure, superheated vapor exists at a higher H than the saturated vapor. So to help in order to solve problems, a separate table is given for superheated water, and the table looks like is given like specific volume, specific internal energy, specific enthalpy, okay, for different pressures, and this is a partial list. So you can do an example. So this is the problem where we have to find the temperature of water at a state 0.5 megapascal, and what we have been given is the specific enthalpy. So the first thing we have to find out what is the state of such a water, because there nothing is mentioned whether this is a compressed liquid or saturated liquid or superheated. The first thing is to identify its state, and you can look at the table, for example. So the first thing which we are going to do is find out the corresponding T sat. We know the T sat from the table. We go back and look at the table A5 where the pressure is given, and you have to find out the saturation temperature. So this is the 500 kilopascal, equivalent to 0.5 megapascal, and the corresponding temperature is here, and the H of G, which is here, is given by this value 2748. So at the corresponding saturation temperature, the enthalpy of the vapor is less than the value which is given, that means enthalpy of the system. So that means H is more than Hg. So this indicates that this particular state should be higher along this red line, because this is at a constant pressure. Okay. So this must be a superheated vapor. Okay. Now what you need to do in order to find the temperature? So you have to go and to the another table which lists all the properties for superheated water. Okay, and you look at it, and then so you will find out somewhere for the case of P equal to 0.5 megapascal. So now you look at again, so this table very carefully. For each of them you have the saturation temperature and the other variables. Okay, so let me again go back. The variables are V, U, H and S. So this is your basically H here. Okay. Now you look at saturation temperature, this is value less than 2890, and increase, then you have to, of course this means as you go away from the saturated vapor line, okay, this temperature is increasing. So along this your temperature increases. So this is where the temperature is increasing here, and here you should see where this value falls. So it falls somewhere in between. This is H. So this is more than 2855.8 but less than 2961.0, and it essentially means the temperature of the system, okay, is somewhere between 200 to 250. Then you can use linear interpolation to find out the temperature, okay, based on your enthalpy values. Okay, so next we are going to discuss is the compressed liquid. Compressed liquid is of course this region, which is left side of the saturated liquid line. Now this is something which can be characterized by higher pressure than the saturation pressure at a given temperature, or lower temperature. For low temperature means less than the saturation temperature at a given pressure. So let's take a look of this pressure which is already given. So this is a pressure 500 kilopascal, and its saturation temperature is this. So this is 0.5 megapascal, right? The saturation temperature is this, and our system lies here. So this is our system. At this system the temperature is 75, but this is at the same pressure, and thus the T here is less than T sat at 0.5 megapascal. So which is the condition of your compressed liquid. So let's again look at this point here. Okay, so if you take this T, okay, this is our T, and if you want this to be T sat, then what would be the corresponding pressure? So somewhere this will be like this. So this will be the pressure which will give you the specific temperature T here. So this will be the temperature, and the corresponding pressure for this particular temperature would be P, which will be less than this value. So that's what he says. So P higher, the pressure here is greater than the P sat, because this will be the P sat for this particular, okay, because this is the point which we are talking about. So this will be the P sat, or this will be the condition for compressed liquid, that the pressure of the system in the compressed liquid should be greater than P at any given temperature, and the temperature should be less than the T sat at any given pressure. Okay. The other important thing which is much easier to understand is that all other properties, whether it's specific volume, specific energy or enthalpy, they are going to be less than the liquid properties, because the compressed liquid is on the left side of the saturated liquid line. So all other properties are going to be less than the fluid properties. Now the compressed liquid depends on temperature much more than they do on pressure, and typically what we approximate compressed liquid is all of the properties are approximated by the corresponding value of the saturated liquid. So that's what we do is Y, or is any property, specific volume, internal energy or enthalpy, this gets approximated by Y of saturated liquid at that particular temperature. But more accurate relation includes this term as well. So this is what we summarize that for a given pressure and temperature, volume is approximated by the saturated fluid value, similarly for internal energy, similarly for H, corresponding saturated properties. So let's end this specific lecture by just looking at the reference state and reference values. Now typically all the properties which we are listed in the tables, such as your particularly specific volume, pressure and temperature, these are very well measurable properties, okay, in the experiment. But internal energy, enthalpy, entropy, they are not. They depend on these other properties which are measurable. Now this is defined by a relations, very sound thermodynamic relations, which tells us that how to calculate the changes in such properties in terms of measurable properties. So what we can do is we can find out the changes in the properties using the measurable properties. So changes in the properties which cannot be measured can be calculated using other measurable properties. So in order to do that, we make use of some reference, because you need some reference value to find out the change. And that's what these tables use, some kind of references. So for example, you can look at the saturated water temperature table. The reference value is a triple point, where we are assuming the saturated liquid internal energy to be 0 and as well as entropy to be 0. Okay, and similarly for refrigerant, the reference temperature is -40, and you can see here the values are considered to be 0. Now as long as you use the same table to calculate the properties in your analysis, the reference value will get cancelled. So essentially, there will be no effect on the reference value. Okay, so that's how we make use of the table. So in summary, the thermodynamics, we are concerned with the changes in the property, and the reference state chosen is of no consequence in calculations. Okay, so in the next lecture we are going to discuss commonly used equation of state.